Okay, section 2.16, theoretical probability. So let's take a look at the Explore section. And it states, they give us what happens is they give us a little chart here, and they tell us the odds of winning a certain lottery. And they give the odds here of matching four and the amounts, all five, and so on and so forth. So A to ask us, well, please find the probability of winning at least $200 by playing this lotto game. Okay, now they kind of start with theoretical probability in the middle of it. There is, um, first of all, symbolization of how to do probability, and that is going to use the symbolization. They want us to find the probability of at least $200. Okay. And I'm going to use some reasoning that, first of all, probability has to be between 0 and 1, or 0% and 100%. And it's explained down here in theoretical probability, little explanation here, the definition. Okay. The probability of an event occurring is the chance of happening and is written as a probability of E. And it has to be between 0% and 100%. Okay, that's theoretical probability. All right, so I want the probability at least $200. Now that's going to equal 100%, or 1 minus the probability of less than, because I know all the probabilities less than $200, which is 3 and 2. 3 of the numbers and 2 of the numbers. So I'm going to go ahead and take 1, or 100%, minus the probability of less than $200. Sometimes it's easier to, because these are equal. Sometimes it's a lot easier to figure out what this one is than this one. And in this case, it is. Okay, so here's how I'm going to do this. I'm going to take 1. I should have left myself some room here. I'll do it over here. So I'm going to take my 1 minus probability of less than 200. And those are, here's my 200, so I need these two probabilities. I'm going to multiply these together. So I told you they kind of jumped ahead with this problem. So 1 over 157 times 1 over 12. And that's going to give me the probabilities of less than $200. So this equals 1 minus, if I use my calculator, I think I did this earlier, I get 0.9995. And when I subtract 1 minus 0.9995, I can do this in my head, I get 0.0005. So in this lotto or lottery game, my chances of winning at least $200, and I'm going to go ahead and write this as a decimal because that's more meaningful to me. Well, my decimal over 2 places, 0.05%. So to win at least $200, I have a 0.5% chance of winning. That's pretty slim. But that's kind of reality with those lottery games. That's why they make so much money and give it to the education system, right? Not politicians' pockets. B, what's the probability that you win something? Oh, so anything. Okay, so the probability of anything. Well, I'm just going to go ahead and multiply all these probabilities together. So going to equal 1 divided by 1 million, uh, 1,221,759. Oh, there's a good percentage of winning something, huh? 1 over 6,109 times 1 over 157 times 1 over 12. I put that all in my calculator. I'm going to get a scientific notation because my calculator is just not going to be able to show that small of a number. Okay, 1 divided by 1,221,759 times 1 divided by 6,109 times 1 divided by 157 times 1 divided by 12. And I get this 7. Okay, this is scientific notation because it's such a small number that uh, that my calculator can't even show it. So the probability of winning anything is going to be point 0, and I'm going to have 14 of these zeros and 7. Well, actually, that doesn't make sense because to win less than $200 is a 0.5%, and this is no percent. So what I should have done here is I should have added these instead of multiplying. Okay. If I do that, here's 8%, here's 0.06%, so on and so forth. Instead of doing this all in a calculator, I'm just going to add all these together, try to do this in my head. So I got 0.08. They were kind enough to put them in decimals. The third number, 0.0639 is 9. Fourth number is 1, 2, 0, 1. 3 is 4, plus 3 is 7. Fifth number is 0, 6 plus 7 is 13, 16. So this is a 6, and this is an 8. And that's as far as I'm going to go. To put this as a percentage, I'm going to roughly somewhere around 9% to win something. Again, that sounds much better than this very small number. Okay, C, if you play this game once a week for a year, so every week I have a 9% chance of winning, it's asking me, are you doing better or worse than expected? If I win something 3 times, so 3 out of 52 weeks, that's what it's asking me. Are you doing better or worse than expected? So let's do 3 divided by 52 weeks. And that gives me approximately 0.06% times of winning when I should have 9%. So doing much worse than expected because I should be doing 9%. All right. So it wasn't that fun. Again, it's theoretical probability where it's the probability of an event occurring and its chance of happening, okay, between 0 and 1. An event of 0%, of course, is impossible, and an event of 100% is a certain event. Okay. And here's a formula for probability, theoretical probability. Number of both favorable outcomes divided by the number of possible outcomes. In other words, they do an example here with die. If I roll one dice, there's six possible outcomes, so that would be my denominator. And suppose they want the number five to show up, well, there's only one five, so one out of six. Number two, suppose you have a bag with four blue marbles, 14 red marbles, and nine green marbles, and you pick one marble out of the bag. What is the probability of picking a blue marble? Okay, so picking a blue, you see five of the marbles are blue, and so the number of favorable outcomes is five, and then the number of possible outcomes. So I need the total number of marbles. Let's see, five plus 14 is 19, plus 8 is 28 total marbles. And again, I'm going to use percentages because that makes the most sense for me. 5 divided by 28 gives me 0.18 or approximately 18%. What is the theoretical probability of picking a green marble? So green, let's see, I have 9 favorable outcomes out of total outcomes of 28. 9 divided by 28 gives me, I should use approximately 0.32 or 32%. Okay, writing the space samples as shown in the next one can help you find theoretical probabilities. Yikes, not my favorites. Find the theoretical probability of getting a sum of 5 when two fair dice are rolled. So again, if I roll two die here, the first die can be 1 through 6. Second die can be the 1 for each number of the face of the die. You do that again, roll 2 for the second die, and so on and so forth. So if I roll, I have the choices of 1 through 6 for the first die, and then 3 for the second die. And then I go and find which ones add up to 5. And my favorable outcomes here is 1, 2, 3, 4. And my total is 36. That's how they came up with 4 out of 36 or 1/9. Always reduce. In order to use the approach shown in the last example, we must be sure that the outcomes in the sample space are equally likely. Using the ratio of that whole favorable outcomes does not have equally outcomes can lead to incorrect probabilities. For example, it is tempting to think about the probability of getting a sum of 5 in the following way. There are 11 different possible sums when you roll two fair dice. Since the sum is 5 out of 11 outcomes, probability is 1 out of 11. Clearly, that's wrong. The probability of an event occurring and the probability of it not occurring sum to 1 or 100%. If there's a 70% chance of rain, then there is a 30% that it will not, adding to that 100%. If we know the probability of getting a sum of 5 is 1/9, then the probability of not getting a sum of 5 is 8/9. How many different outcomes are possible when 3 fair coins are flipped? Are they equally likely? Okay, so um, the, we're going to do this just like they did with the chart. So the first time I can get heads, 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 tails, or I can get um, tails. I should say heads, heads. Okay, so the first flip I can get heads, heads, heads. Then the second, or I can get heads, heads, tails, or I can get heads, tails, heads. How about, I should try to keep this neat. Let's see, heads, 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 tails, heads, tails, heads, and then tails, heads, heads. And what about tails, tails, heads? And let's see, how about tails, tails, tails? And let's see, how about the first one I can get a heads. Second one, I can get a tails. I suppose I should have did this in a better order. Tails instead of the heads. What if I get a heads, let's see, do I have a tails, tails, heads? Yes, I do. Uh, tails, heads, tails. Should be one more. What am I missing? Um, tails, heads, heads. Tails, tails, heads, tails, 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 tails. Let's see. Nope, I think that's it. 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Are they equally likely? Yes. What is the probability of flipping 3 fair coins and getting all heads? Well, the only way I can get all heads is 1 out of the 8. So 1/8 all heads. Okay. What is the probability of not getting all heads? Well, 1 minus 1/8 is going to be 9/8 for not all heads. Remember, they have to add up to 1. And what is the probability of getting at least one of each heads and tails? So this one might have C. At least one of each heads and tails. So 1, this one has a tail. So 2, 3, 4, 5, 6 out of 8. Please reduce, or not please, you must reduce. I get 3/4 of at least one head or tail. If you flip 3 fair coins 10 times and get only heads only once, how does this experimental probability compare to theoretical probability? Well, my theoretical probability would be for 10 times and 3 for and get all heads. So my all heads is 1/8. So if I did that 10 times, let's see, 1/8. Again, I'm going to just real quick make this a percentage. 0.12 or 12.5%. And and I only get heads once. How does this experimental probability compare to the theoretical? So theoretical probability says um, that it would be 12.5% or 1/8. Okay. The experimental probability says I got, let's see, 10 times. So I got one out of the probability that it could have been was, so those 10 flips gave me how many outcomes, how many favorable outcomes. Well, I had eight per flip. So 8 times 10 flips is 80. So my experimental probability came out to, if I make that a percentage, again, it's easier for me to see. I get 1.25%. So how does it compare? Well, obviously I got much, much less than the 12.5%. All right. The last problem makes an important point that experimental and theoretical probability for the same event can be and often are different. The experimental probability tells us that what percent of the time something actually happens, whereas a theoretical um, probability tells us what percent of the time we expect the event to happen. Usually, more times an experiment is conducted, the closer to the experimental property gets a theoretical probability. Okay, so that's very true. We only did this 10 times. If I did this 100 times or even 1,000 times, I would expect this experimental property, and it will, get closer to 12.5%. Go ahead and flip 3 coins for 1,000 times. You can prove it. Suppose there's a raffle with numbered tickets. One ticket is randomly drawn out of a hat. Your ticket is number 121. Find the probability of winning. State your answer as a fraction, a decimal, and a percent. There are 200 tickets. What are your chances of winning? So I got one ticket right. Yeah, 1 out of 200 tickets. So there's my fraction. So we're going to put that in the calculator. 1 divided by 200. My decimal is 0.005. And that is a decimal over half a percent. There are 400 tickets. So 1 out of 400 is 1 divided by 400, 0.0025, with the decimal over, or 1/4%. If there are 1,000, 1 divided by 1,000, 0.001, or 1,000. And we have 0.1%. What happens to your chance of winning as the number of tickets sold increase, your percentage goes down of winning. And why does that happen? Well, for obvious reasons. Okay, there's more tickets to choose from. If 150 tickets were sold in a raffle, how many tickets would you need to buy and have a 10% chance of winning? Well, 10% of 150, it's kind of almost doing your head. So we want to take 50 tickets and I'm going to multiply it by 10% or 0.10. All I'm going to do is move that decimal. Oh, sorry, 150. I need to purchase 15 tickets. When the possibilities are small, it's helpful to use place value to interpret in a meaningful way. 0.25% and or 25 out of 10,000. All right. Suppose a local restaurant is running a dart competition for the contestants will be blindfolded. The owners want to do something fun. Consider three non-traditional options for paper tire. Number five, we show a picture of a dartboard and the other options. Hitting a bullseye is defined as hitting the shaded area of the dartboard. For each target, find the chance of hitting a bullseye by calculating the ratio of the shaded area to the total area. And then to convert each probably to a decimal around the two places and then to a percent. For which target would you find the greatest chance of hitting the bullseye? Is that what you expected? Okay, so this actually might be a little bit of some work here. Okay, bullseye is defined as hitting any of the shaded areas. So for total areas, what we're going to have to do here is for the shaded areas in each one, we need the total area for the circle. So the total area is pi r squared and or pi diameter. So pi r squared here is going to be pi, let's see, 9 squared. Okay, my radius is r, half of 18, so total for the circle is 81 pi. We'll go ahead and multiply that out. 81 times pi is 254.47 square inches. Okay, so the first one, I'm going to take my total of the big circle minus the shaded area. The shaded area here is a square. So the area of the square is going to be 6 times 6, which equals 36 square inches. So my um, my rest of the area here is going to be, well, actually, we're trying to find the probability, so I'm going to do 36 out of 254.47 favorable outcomes out of total outcomes. Remember the formula. So 36 divided by 254.47. So this is going to equal 0.14 or approximately 14%. Okay, B. I've got these 3 by 3 little squares. So this is 9, 9, 9 square inches and 9 square inches. Or in other words, um, again, I'm going to have 36. 9 plus 9 plus 9 plus 9 is 36. And we're going to get 36 out of 254. Again, we're going to get about 14%. It's the same problem. They just split up that 36 into 9 different squares. Okay, small circle here. Small circle is going to be the area of the small circle is pi r squared. My r is 3 squared pi. So 9 pi, area of small circle. So 9 pi is 28